August 27th, 948 AD. A chieftain's feast hall in western Norway. 300 warriors have gathered to celebrate a successful raid. The cooks have been preparing for 2 days, a whole ox in the earth oven, dozens of fish on hot stones, barrels of ale fermented for weeks. The feast begins. Within an hour, 70 warriors are violently ill, vomiting and convulsing. By morning, 12 are dead, including the chieftain's eldest son. What killed them? The cooks had used the wrong stones, porous river rocks that absorbed water over years. When heated red hot and plunged into the cooking trough, microscopic steam explosions inside the stones shattered them into razor-sharp fragments, too small to see, but large enough to shred internal organs. When swallowed, the head cook was executed by Blood Eagle the next day for his fatal mistake. In Viking culture, cooking a feast wasn't just culinary art. It was life or death engineering, where one wrong decision could massacre your entire leadership, destroy your reputation forever. Here's what nobody tells you about Viking feasts. Popular culture shows endless roasted meat and overflowing ale horns like it's a medieval buffet. The reality, cooking for 300 warriors using nothing but stone and fire without any metal cookware, was one of the most dangerous, technically complex operations in Viking society. You couldn't just throw meat on a fire and hope for the best. Every step, from selecting stones, to managing fire temperature, to timing the cooking of multiple dishes, simultaneously required knowledge so precise that it took decades to master. One mistake, using wet stones, getting fire temperature wrong, miscalculating earth oven timing, contaminating the ale fermentation could poison hundreds of people, start fires that burn down the entire settlement, or create food so inedible that warriors would consider it an insult worthy of violence. The chieftain who hosted a failed feast didn't just lose face, he could lose his position, his clan's loyalty, and potentially his life. What I'm about to show you isn't some romantic notion of primitive campfire cooking. This was sophisticated thermal engineering, material science, microbiology, and project management, all wrapped into one survival-critical skill set. Vikings developed cooking technologies so advanced that modern survival experts and experimental archaeologists struggle to replicate them. Successfully, they could slow cook an entire bull underground, using nothing but heated rocks, and achieve temperature control so precise the meat would be fall off the bone tender after 18 hours. They could fry fish on flat stones, heated to exact temperatures that modern chefs achieve with thermostats. They could maintain boiling water in wooden containers for hours without burning them. They could preserve food through controlled smoking that prevented bacterial growth, while creating flavors that would impress any modern chef. And they did all of this without thermometers, without timers, without any modern safety equipment. Under immense pressure, knowing that failure meant disgrace or death. Stay with me. Because the first secret to Viking cooking isn't technique. It's understanding which stones will cook your food and which stones will explode, kill you. Let me tell you about the single most dangerous element in Viking cooking that everyone ignores: stone selection. You're thinking, how dangerous can rocks be? Let me answer with a scenario. You're preparing a feast. You've spent 2 days gathering ingredients, butchering animals, preparing the earth oven. 300 warriors are arriving in 6 hours. You need to heat stones for boiling water to cook the stew. You grab stones from the nearest riverbank, because they're smooth and perfect sized. You heat them red hot, approximately 700 degrees Celsius. You plunge them into the wooden cooking trough. Three things happen simultaneously. First, the water inside the stone's porous structure instantly converts to steam, generating pressure of approximately 160 atmospheres. Second, the stone explodes with the force of a small grenade, sending superheated rock fragments flying in all directions at lethal velocity. Third, anyone standing within 3 meters gets hit with stone shrapnel that can blind, maim, or kill. I'm not exaggerating. Archaeological evidence shows Viking-era injuries consistent with stone fragmentation trauma. The Vikings learned through brutal trial and error which stones were safe and which were death traps. Porous stones, anything that absorbed water, like sandstone, limestone, shale, or river-worn stones that had been submerged, were absolutely forbidden for cooking. These stones contained microscopic water pockets that created steam bombs when heated. The catastrophic failure wasn't gradual. It was instantaneous explosion that could destroy your entire cooking operation and injure everyone nearby. Safe stones were dense, non-porous rocks with tight crystalline structure that had no water absorption. Granite was ideal. Its interlocking crystal structure distributed thermal stress evenly. Basalt was perfect. Volcanic origin meant it had already withstood extreme temperature changes. Quartzite worked well. Metamorphic transformation had compressed it into stones so dense that water couldn't penetrate. But here's the catch. You couldn't just identify the rock type visually. Vikings developed empirical testing protocols. Candidate stones were collected from dry, elevated locations far from water sources. They were stored in covered wood piles for months to ensure complete drying. Even good stones could retain moisture if freshly collected. Before using a new stone in actual cooking, it was test-fired, heated gradually, and observed for any cracking, spalling, or moisture release. Stones that passed this test were marked and guarded as precious cooking equipment. A collection of proven cooking stones was as valuable as any metal tool. The fire management was equally sophisticated and dangerous. Vikings didn't have a fire. They maintained multiple fires simultaneously, with different heat outputs calibrated for specific cooking tasks. The spit roasting fire was massive, consuming entire logs, generating intense radiant heat, but kept at specific distance from meat. Too close, and you carbonize the exterior while leaving the interior raw and potentially dangerous with parasites. The stone heating fire was different. Medium intensity fire maintained at steady temperature for hours. Heating cooking stones to precise temperatures. Too hot and stones would crack from thermal shock. Too cool and they wouldn't retain enough heat for effective cooking. The smoking fire was barely alive, smoldering embers, producing thick, cool smoke without flames. If it flared up, you ruined the preservation process by cooking the meat instead of smoking it. Managing these multiple fires simultaneously while monitoring stone temperatures, meat doneness, and smoke density required a team of experienced cooks working in perfect coordination. One person's mistake could cascade through the entire operation, causing disaster. The fuel selection mattered as much as the fire management. Different woods produce different heat outputs, burning durations, and smoke flavors. Hardwoods, like oak and beech, were premium fuel. They produced intense, long-lasting heat with minimal smoke and ash. Birch was valuable for its fragrant smoke used in both cooking and preservation. Pine and other resinous woods were generally avoided for cooking because they produced acrid smoke that contaminated food flavor and deposited sticky resins. But in fuel-scarce regions, any wood was precious. Vikings had to calculate fuel needs for multi-day feast preparation. A single earth oven operation could consume the equivalent of 15 to 20 full-grown trees just for the initial stone heating phase. Running out of fuel halfway through cooking meant ruined food and failed feast. The pressure on the fuel gatherers was enormous because they enabled everything else. Can you imagine the stress of knowing that if you miscalculated fuel needs, tomorrow's feast for 300 warriors would fail, and the chieftain would blame you? But fire and stones were just the foundation. What Vikings did next, cooking entire animals underground, seems like magic until you understand the physics. Picture this scene. You need to cook a 300-kilogram bull to perfect tenderness for tonight's feast. You have no oven, no metal pot large enough, no way to rotate something that massive over a fire. The meat is tough. This animal spent its life working, building dense muscle fibers that will be inedible if simply roasted. How do you transform this into fall-off-the-bone tender meat, using only a hole in the ground and hot rocks? The answer is the grop, the earth oven. And it's one of the most sophisticated cooking technologies ever developed. But here's what makes it dangerous. 1. Miscalculation in timing or temperature, and you've just created 300 kilograms of rotten meat that will kill everyone who eats it. Let me explain the engineering that separates success from catastrophic failure. The earth oven construction began days before cooking started. Diggers excavated a pit sized to accommodate the food for a whole bull. This meant a trench 2 meters wide, 3 meters long, and 1 meter deep. The excavation had to account for stone layers, meat volume, and insulating materials. Too shallow and heat escaped upward, cooking food unevenly. Too deep, and you couldn't extract the cooked food without destroying it. The pit walls were sometimes plastered with clay to prevent collapse and improve heat retention. At the bottom came a thick layer of proven cooking stones, the same dense, dry granite or basalt that passed all safety tests. These stones were arranged carefully to create maximum surface area for heat transfer. A massive fire was built directly in the pit and burned for 8 to 12 hours, sometimes through an entire night, until the stones glowed red hot, and the pit walls themselves became fired ceramic from the intense heat. This stone heating phase required constant fire feeding and monitoring. The goal was achieving approximately 500 to 600 degrees Celsius stone temperature, hot enough to maintain cooking temperature for 18 to 24 hours, but not so hot that they'd crack from thermal shock when moisture hit them. When the stones reached target temperature, the real danger began. The coals and ash had to be cleared out quickly, without cooling the stones significantly. This was done with long-handled wooden shovels and rakes, workers approaching as close as they could tolerate to the radiating heat. Burns were common. The pit was radiating heat like an open furnace. Then came the critical insulation layer, fresh, damp leaves, usually bog, maple, or fern, laid thick over the hot stones. This layer had multiple purposes. It prevented direct contact between meat and stones that would char the exterior. The moisture in the leaves converted to steam, creating a moist cooking environment. The steam carried heat into the meat more effectively than dry air. But here's the danger. If leaves were too wet, They'd generate excessive steam that could disturb the stone layer or create hot spots. If too dry, they'd ignite and fill the pit with flame instead of steam. The prepared meat went in next. For a whole animal, this meant extensive preparation. The carcass was gutted and cleaned. Salt was rubbed thoroughly into all surfaces and cavities. This served multiple purposes, including seasoning, antimicrobial action, and moisture control. Wild herbs were stuffed into body cavities: juniper, wild garlic, cumin, providing flavor and antimicrobial properties. The entire carcass was wrapped in multiple layers of damp cloth or clean animal skins to protect it from direct heat and retain moisture. Lowering 300 kilograms of wrapped meat into a pit full of radiating hot stones required coordinated effort from multiple people using wooden poles and leather straps. One slip and you've destroyed hours of preparation, possibly injured workers, and ruined the feast. More layers of damp leaves were packed around and over the meat, creating complete insulation. The critical final step was sealing. The entire pit was covered with layers of earth and turf, creating an airtight seal that trapped heat and steam inside. The covering had to be thick enough to prevent heat escape, but porous enough to prevent pressure buildup that could disturb the cooking environment. Now came the waiting and the terrifying uncertainty. Once sealed, the earth oven couldn't be opened for verification without ruining the entire cooking process. You had to trust your calculations. For a whole bull, cooking time was typically 18 to 24 hours, depending on pit size, stone mass, and meat quantity. Too little time, and the interior was undercooked. Consuming undercooked pork or bear meat could give you trichinosis that would kill you slowly and agonizingly. Too long, and the outer meat became mushy, and the inner meat potentially began bacterial growth if temperature dropped below safe zones. Vikings calculated cooking time empirically based on meat size, pit size, and previous experience. But variables existed: outside air temperature, wind cooling the earth mound, moisture in the soil, conducting heat away faster than expected. The feast cooks spent those 18 hours in nervous anticipation, knowing they couldn't verify success until the pit was opened. The moment of truth came when the earth covering was carefully removed. The steam and smoke cleared, and the wrapped meat was extracted. The smell told you immediately if you'd succeeded or failed. Properly cooked meat produced an incredible aroma of herbs, smoke, and rich meat juices. Failed cooking produced the sickening smell of putrefaction that meant disaster. When successful, the result was extraordinary. Meat so tender, it fell apart at the touch, infused with herbal flavors, retaining all its natural juices. Warriors would praise the cooks as much as successful raid leaders. When failed, the consequences were severe. But earth ovens weren't the only cooking method. For faster cooking and different textures, Vikings used techniques that seem impossibly simple but required perfect execution. Imagine you're a Viking cook and you've just caught 30 salmon that need to be prepared for tonight's feast in 6 hours. You have no metal pan, no modern stove, nothing but fire and stones. How do you cook 30 fish perfectly without burning them, drying them out, or having them stick to whatever surface you're cooking on? The answer seems absurdly simple: flat stone frying. But the execution separates masters from amateurs who create inedible, charred disasters. Let me show you the precision required to make this work. The stone selection for frying surfaces was even more critical than for heating stones. You needed large, flat stones, ideally 30 to 50 centimeters diameter, with smooth surfaces and uniform thickness of about 5 to 8 centimeters. The thickness mattered because thin stones would heat unevenly, creating hot spots that burned food. Thick stones took too long to heat and retained too much thermal mass that couldn't be modulated. The surface had to be naturally smooth. Any rough texture would cause sticking. Vikings sought out specific river stones that had been naturally polished by water erosion over decades, creating glass-smooth surfaces. These stones were rare and valuable. A collection of good frying stones was prized cooking equipment, passed down through generations. The preparation process was exacting. The selected stone was thoroughly scrubbed with sand and water to remove any organic matter or mineral deposits. Then it was calcined, heated very hot in fire for about an hour. This process served multiple purposes. It drove out any moisture trapped in the stone, preventing explosive failure. The heat sterilized the surface, killing any bacteria. The thermal cycling changed the surface chemistry slightly, making it somewhat more non-stick. After calcining, the stone was allowed to cool completely, then heated again to cooking temperature before use. Achieving the correct cooking temperature required skill developed through years of practice. The target was approximately 180 to 200 degrees Celsius for fish, hot enough to sear the surface quickly, cool enough that the interior cooked through before the exterior carbonized. Vikings tested stone temperature using the water drop test, a technique still used by blacksmiths and chefs. A few drops of water placed on the stone would dance and evaporate in characteristic patterns based on temperature. At correct cooking temperature, water drops would skitter across the surface for several seconds before evaporating. This indicated the Leidenfrost effect was occurring, meaning the surface was hot enough for effective searing. Too cool and water just sat and boiled away slowly. Too hot and water exploded instantly into steam. The stone was removed from the fire at optimal temperature and placed on a bed of coals that maintained heat without adding more. The fish preparation was minimal but essential. Salmon or trout were left whole and ungutted. The scales and skin provided natural protection. The outside was patted completely dry. Any surface moisture would cause steaming instead of searing, ruining the texture. The fish was placed directly on the hot stone. The immediate searing sound told you if temperature was correct. A sharp sizzling indicated proper heat, while silence meant too cool and burning smell meant too hot. The scales and skin seared instantly, creating a protective carbonized layer that prevented the delicate meat from sticking. The fish was left undisturbed for 3 to 4 minutes. Moving it prematurely would tear the flesh. When ready to flip, a thin wooden spatula was slid underneath with a firm, quick motion. The cooked side released cleanly if done correctly. The result was restaurant-quality fish, crispy skin that peeled away easily, meat that was perfectly cooked through, moist and flaky, infused with light smoke flavor from the fire. The absence of added oils meant pure fish flavor, enhanced only by salt and herbs. Modern non-stick pans can't replicate this texture because they don't get hot enough and they add metallic flavors. The same flat stone technique worked for flatbreads that were dietary staples. A simple dough made from barley or rye flour, water, and salt was formed into thin discs about half a centimeter thick. These were thrown directly onto hot stones, where they puffed up as internal moisture converted to steam, creating light, crispy flatbreads in 2 to 3 minutes. This bread was the perfect accompaniment to every meal. It soaked up meat juices, wrapped around vegetables, or was eaten plain with butter. The production rate was impressive. An experienced cook could produce one flatbread every 3 to 4 minutes, meaning 60 to 80 breads per hour. For a feast feeding 300 people, you needed multiple cooks working multiple stones simultaneously to produce adequate bread. The logistics were as complex as any military operation, coordinating who worked which stones, maintaining fire temperature across multiple cooking areas, timing bread production so it finished fresh just before serving. Can you imagine managing 10 workers, each producing bread at different rates, each kneading stones at specific temperatures, all needing to finish simultaneously? Yet this was standard feast preparation. But cooking on stone surfaces was just one method. For soups, stews, and boiling water, Vikings developed a technique that seems physically impossible until you understand the thermal physics. Here's a cooking technique that violates everything modern people think they know about physics. Boiling water in a wooden container that should catch fire seems impossible. Right wood burns. Fire boils water. Therefore, fire plus wooden pot equals disaster. But Vikings boiled water in wooden troughs for hours without burning them, using a technique so clever that modern engineers are impressed when they see it demonstrated. This method also happens to be one of the most labor-intensive, dangerous cooking operations they performed. Let me explain the hot stone boiling method that cooked soups and stews for hundreds of warriors. The cooking vessel was typically a large wooden trough carved from a single log, basically a dugout canoe, repurposed for cooking. These troughs were massive, often 2 meters long, 60 centimeters wide, and 40 centimeters deep, capable of holding 100 to 150 liters of liquid. The wood had to be dense, hardwood like oak, that could withstand repeated thermal shock. The trough was filled with water, chopped meat, root vegetables, and salt. This was the base for the stew. Obviously, you couldn't build a fire under a wooden trough. It would burn immediately. Instead, Vikings brought the fire to the water using heat transfer stones. A large fire was maintained constantly nearby, with a bed of stones heating in the hottest part of the flames. These stones were specifically selected medium-sized rocks, approximately 10 to 15 centimeters diameter, large enough to hold substantial heat, small enough to handle safely. When stones reached red-hot temperature, approximately 600 to 700 degrees Celsius, they were extracted using long wooden tongs and quickly transferred to the cooking trough. The moment a red-hot stone hit the water was violent and dangerous. The water immediately adjacent to the stone flash-boiled, exploding into steam bubbles that sent scalding spray in all directions. The entire trough erupted in roiling boil around the stone. The temperature differential, 700-degree stone hitting 20-degree water, created thermal shock that would shatter inferior stones, sending fragments through the stew and potentially into people's throats when served. The noise was tremendous, hissing, bubbling, steam escaping. The cook managing the stone transfer had to work fast to minimize heat loss while avoiding steam burns. The stone gave up its heat rapidly, cooling from 700 degrees to water temperature in approximately 5 to 10 minutes. During this time, it transferred enormous thermal energy to the water, raising the temperature of the entire trough contents by 5 to 10 degrees per stone. depending on trough size and water volume. Here's where the labor intensity became extreme. To maintain a continuous boil for hours, stones had to be added continuously in rotation. One stone cooled out. Another red-hot stone went in immediately. This required at least 3 to 4 people working in perfect coordination. 1 or 2 people constantly fed wood to the heating fire and monitored stone temperatures using long poles to position stones in the hottest zones. Another person extracted red-hot stones using tongs and delivered them to the cooking trough. This was the most dangerous position. Working directly with stones that would carbonize flesh on contact. Another cook managed the trough, removing cooled stones and directing incoming hot stones to different areas to ensure even heat distribution. For a large feast requiring multiple troughs cooking simultaneously, you needed crews of 10 to 15 people just managing the hot stone logistics. This wasn't cooking. This was industrial thermal engineering using human labor to move heat energy from combustion source to food. The method's brilliance was in the temperature control it provided. Unlike a fire directly under a pot, which creates hot spots and burning, stone, boiling, distributed heat throughout the liquid. Each stone heated a spherical zone around it, and multiple stones overlapped to create relatively even temperature. The cook could modulate temperature by adjusting stone addition rate. More stones per hour meant hotter cooking. Fewer stones meant gentle simmering. This allowed the same trough to be used for different recipes. Tough meat required vigorous boiling for hours to break down collagen. Delicate vegetables needed gentler heat to avoid mushiness. The stone boiling method accommodated both by varying stone frequency. The resulting stew was extraordinary. The constant thermal cycling as stones were added created convection currents that mixed the stew naturally. Meat and vegetables cooked evenly. The mineral content from the stones added a subtle flavor complexity that's impossible to replicate. The slight smoke taste from ash on the stones added another flavor dimension. What seems like primitive technology actually created complex flavors that modern cooking struggles to match. But boiling in wooden troughs and frying on flat stones still left one critical question. How do you roast an entire animal perfectly when you can only access it from outside? The answer involves fire management, so precise it would impress any modern chef. Imagine being responsible for spit roasting a whole boar over an open fire for 300 warriors who will literally kill you if the meat is undercooked and gives them parasites, or overcooked and insults their chieftain's feast. This animal weighs 150 kilograms. It must cook evenly throughout the haunches, the shoulders, the belly, the back. You have no thermometer, no timer, no temperature control except fire positioning and rotation speed. The entire process will take 12 to 16 hours of continuous attention. One moment of inattention and a year's worth of preparation is ruined. This wasn't cooking. This was engineering masquerading as cuisine. And the penalty for failure was severe. Let me show you the precision required to roast meat perfectly, using nothing but observation and experience. The fire construction for spit roasting was massive and precisely engineered. This wasn't a campfire. This was a combustion system, 3 to 4 meters long and 1 meter high, burning continuously for 12 to 16 hours. The fire had to be built with hardwood that produced intense radiant heat without excessive flame that would char the exterior. Oak and beech were premium fuels producing steady heat output. The fire was constructed in a long trench or lined pit that reflected heat upward toward the meat. The geometry mattered. The trench concentrated heat and prevented wind from disrupting the thermal environment. The initial burn phase took 2 to 3 hours. Burning down logs to establish a deep bed of hot coals that provided steady, radiant heat without flames. Flames were the enemy. They created uneven heat, generated soot that contaminated meat, and couldn't be maintained steadily for hours. Coals were the goal, glowing embers radiating infrared heat evenly. The spit itself was a massive wooden pole, typically a straight hardwood beam, 8 to 10 centimeters in diameter, strong enough to support 150 kilograms without bending significantly. The boar carcass was prepared by gutting and cleaning, then seasoning inside and out with salt and crushed juniper. Metal skewers didn't exist, so the animal was bound to the spit using soaked leather straps and wooden pins that held it secure during hours of rotation. The critical decision was distance from the fire. Too close and you'd carbonize the exterior, while the interior stayed raw and potentially dangerous with trichinella parasites that caused excruciating death. Too far, and you'd never reach sufficient internal temperature to cook through before the exterior dried out into leather. Vikings determined optimal distance, empirically, approximately 60 to 80 centimeters above the coal bed. At this distance, radiant heat from coals slowly penetrated the meat, cooking from outside inward at a rate of roughly 1 centimeter per hour depth of penetration. For a boar with 20 centimeter thick haunches, you needed 20 hours of cooking to ensure the deepest tissue reached safe temperature. The rotation requirement was absolutely critical and brutally exhausting. The spit had to be continuously rotated, quarter turn every 10 to 15 minutes, to ensure even heat exposure on all sides. Stop rotating, and the bottom would char, while the top stayed raw. The rotation was powered by human labor, typically 2 to 3 people in shifts, continuously turning the spit handles for 12 to 16 hours straight. This wasn't light work. 150 kilograms of animal on a long lever arm required significant strength to rotate. Young men considered this task a test of endurance, spending hours turning meat while heat from the fire made the work area unbearably hot. The rotation created a self-basting effect. As the boar heated, internal fats melted and migrated toward the surface. The rotation distributed these fats evenly across the exterior, creating a natural basting that kept the surface moist and added flavor. Fat dripping onto the coals below vaporized, rising back up as smoke that flavored the meat. This cycle of rendering, dripping, and smoke infusion created flavor complexity that can't be replicated any other way. The basting protocol added another layer of complexity. Throughout the cooking process, the meat was regularly brushed with additional liquids to prevent drying and add flavor. The basting liquid was typically ale or beer. The alcohol evaporated, but the malt sugars caramelized on the surface, creating a delicious crust. Honey dissolved in ale created a sweet glaze. Salt water with crushed herbs added flavor and promoted surface crisping. The basting required climbing near the intensely hot fire with brush and bucket, coating the rotating meat thoroughly, then retreating before being overcome by heat. This operation happened every 30 to 40 minutes for 16 hours, requiring remarkable heat tolerance. The monitoring for doneness used multiple indicators. The surface color changed from pink to golden to deep brown as cooking progressed. The aroma evolved from raw meat to roasting meat to fully cooked with caramelized exterior. The feel changed. Experienced cooks could poke the meat with wooden skewers and judge internal doneness by resistance. The juice color when meat was pierced told the story. Red meant raw. Pink meant close. Clear meant done. But the ultimate test was experience. Master cooks developed an intuitive sense of when meat was perfect, based on thousands of hours watching, smelling, and tasting. When finally done and removed from the spit, properly roasted meat was an achievement as impressive as any crafted weapon. The exterior was caramelized and crispy. The interior was tender and juicy throughout. The flavor was complex from hours of smoke infusion and basting. Can you imagine the pressure of spending 16 hours cooking one animal, knowing that failure meant disgracing your chieftain in front of 300 warriors? Yet, this was routine feast preparation. But roasting meat perfectly still left one problem. It would spoil within days unless preserved. For that, Vikings turned to their most sophisticated food science, controlled smoking that transformed fresh meat into food that could last months. Here's where Viking food technology becomes genuinely sophisticated enough to impress modern food scientists. They had figured out how to use smoke as a chemical preservative that created an antimicrobial barrier on food surfaces while adding flavor. Complexity. This wasn't accidental. It was deliberate application of chemistry they didn't have words for, but absolutely understood through empirical chemistry. Observation. They practiced two completely different smoking techniques for different preservation goals. And screwing up either one meant losing your entire winter food supply and potentially starving before spring. Let me explain the difference between hot smoking and cold smoking, and why confusing them could kill you. Hot smoking was the quick method used for immediate consumption. Fish or meat was hung approximately 1 to 2 meters above a hot fire, producing both heat and thick smoke. The temperature in the smoking chamber was approximately 60 to 80 degrees Celsius, hot enough to actually cook the protein, while simultaneously depositing smoke compounds on the surface. The process took 6 to 12 hours, depending on meat size. The result was fully cooked meat with golden brown exterior, smoky flavor throughout, and significantly reduced moisture content. This meat was delicious and ready to eat immediately. But it only lasted 3 to 5 days before spoiling, because the smoking time wasn't sufficient to create the antimicrobial barrier needed for long-term preservation. Hot smoking was perfect for feasts where immediate consumption was planned. The hot smoke rapidly cooked large quantities of fish from a successful fishing trip, making it ready for that night's feast. But for winter survival, hot smoking was worthless. You needed something completely different: cold smoking, that preserved food for months. Cold smoking was genuine food science engineering that required understanding concepts Vikings didn't have vocabulary for, but absolutely comprehended functionally. The goal was depositing large amounts of antimicrobial smoke compounds onto food surfaces, while keeping temperature low enough that the food didn't actually cook. This required separating the fire source from the smoking chamber through a long underground tunnel. The typical cold smoking system was a trench, 3 to 5 meters long, dug underground, approximately 30 centimeters wide and deep. At one end was a fire pit, where a small, smoldering fire burned continuously. At the opposite end was the smoking chamber, either a pit covered with turf or a small wooden hut where prepared meat hung on poles. Smoke from the fire traveled through the underground tunnel, cooling as it went. By the time it reached the smoking chamber, it was below 30 degrees Celsius, cool enough that it wouldn't cook the meat. The smoke density in the chamber was thick enough to be almost opaque, This density was critical for depositing sufficient preservative compounds. The meat preparation before smoking was essential. Fish or meat was soaked in strong brine, saturated salt solution, for 12 to 24 hours. This drew moisture out of the tissue through osmosis and deposited salt throughout the flesh. Salt alone is antimicrobial, killing or inhibiting bacterial growth. The brined meat was then rinsed and hung in the smoking chamber, where it would remain for 5 to 10 days in continuous cool smoke. The combination of salt and smoke compounds created a multi-layer preservation system. The salt controlled moisture and directly killed bacteria. The smoke deposited phenols, formaldehyde, and other compounds on the surface that created a chemical barrier impervious to bacterial invasion. The slow moisture loss from continuous air circulation and smoke exposure further reduced water activity below levels bacteria need to grow. The result was meat that could be stored at cool ambient temperature for 6 months or longer without spoiling. This was the food that enabled Viking long-distance voyages. Ships carried tons of cold smoked fish that provided protein for months at sea. The fire management for cold smoking was exacting and required constant attention day and night for the entire week or more that meat was smoking. The fire couldn't be allowed to flame up. Flames generated excessive heat that would cook the meat instead of preserving it. The fire couldn't be allowed to die. Interruption in smoke flow would allow bacterial growth to start. The ideal fire was smoldering, barely alive coals continuously producing thick smoke. This required adding specific materials in exact quantities. Hardwood sawdust was common. It smoldered slowly, producing dense smoke. Wet wood chips generated cooler smoke. Juniper or alder wood produced smoke with specific flavor compounds that Vikings preferred. The fire tender's job was monitoring smoke density, temperature, and adding fuel incrementally every few hours around the clock for 7 to 10 days continuously. One person's inattention could ruin hundreds of kilograms of meat, representing months of protein for an entire community. The psychological pressure was enormous because you worked essentially alone in the dark, feeding a fire and checking meat. Unable to definitively verify success until the end, when you either had preserved food or rotting disaster. The verification of successful preservation came from multiple indicators. Properly cold smoked meat developed a dark mahogany color and distinctive resinous smell from the smoke compounds. The surface felt dry and slightly tacky. The meat had lost approximately 30 to 40% of its original weight through moisture evaporation. Most critically, it showed no signs of spoilage, no off odors, no sliminess, no mold growth. Improperly smoked meat failed these tests, showing subtle signs of bacterial action that would accelerate into full rot within days. The difference between success and failure was often subtle, requiring experienced observation. When successful, cold smoked fish or meat was hard, almost board-like in texture, requiring soaking before consumption. But it was stable, safe protein that enabled winter survival and long voyages. This preservation technology was as important to Viking expansion as their ships without cold smoking. They couldn't have made weeks-long ocean voyages or survived Arctic winters. Can you imagine developing this sophisticated chemical preservation technology through pure trial and error without any understanding of chemistry or microbiology? Yet Vikings did exactly that, refining the process over generations. But meat preservation was only one piece of the feast puzzle. They also needed bread, and for that they built ovens that would impress modern pizza makers. Making bread seems simple until you try doing it without metal pans, without a modern oven, using only clay and fire. Vikings built clay dome ovens that functioned so well they're essentially identical to modern wood-fired pizza ovens that professional chefs pay thousands of dollars for. These ovens could bake dozens of loaves simultaneously, achieving even temperatures and perfect crust development that rivals modern baking technology. But building one required knowledge of materials, science, and thermal engineering. Let me explain the construction and operation of these ovens that were critical feast preparation tools. The oven construction began with framework. Flexible willow branches were bent into a dome shape, approximately 1 meter diameter and 60% centimeters high, creating a beehive-shaped skeleton. This framework was temporary. It would burn away during firing. The dome was covered with multiple layers of clay mixture, local clay mixed with sand for thermal stability, and chopped straw for structural reinforcement. The first layer was thick, about 5 centimeters, packed tightly against the willow framework. Subsequent layers were thinner, built up over days as each layer dried. The total wall thickness was typically 10 to 15 centimeters, thick enough to retain heat for hours, but not so thick that initial heating took excessive fuel. A door opening was left at the front, approximately 30 centimeters square. This would be sealed during baking. A small chimney hole was built into the top of the dome for smoke escape during the initial firing. The drying phase was critical. Rush the drying, and the clay would crack catastrophically during firing. A properly constructed oven dried for 1 to 2 weeks in ambient air, allowing the clay to cure and the straw reinforcement to bond with the matrix. When fully dried, came the firing phase. A large wood fire was built inside the dome and burned for 8 to 12 hours. This served multiple purposes. The heat burned away the willow framework, leaving a hollow dome. The intense heat, reaching 600 to 800 degrees Celsius, transformed the clay through ceramic firing, converting it from soft clay into hard ceramic material through sintering. The fire also drove out any remaining moisture and thermal cycled the structure, revealing any cracks or weaknesses. An oven that survived this firing would last years with proper maintenance. Ovens that cracked during firing were structural failures that had to be rebuilt. The baking operation required perfect timing and temperature judgment. Hours before baking, a large fire was built inside the oven and burned until the interior walls glowed dull red, approximately 400 to 500 degrees Celsius. This heating phase took 2 to 4 hours, depending on oven size and fuel type. Oak gave best results, steady heat output without excessive flame. When the walls reached temperature, the oven was ready. All coals and ashes were swept out completely using long wooden tools. Any remaining ash would contaminate the bread. The interior walls at this point were glowing hot and white. The floor temperature was checked using the flour test. A pinch of flour was thrown on the floor. If it browned slowly, temperature was perfect. If it carbonized instantly, the oven was too hot and needed to cool slightly. If it just sat there, the oven needed more heating. The bread dough, made from barley or rye flour, water, salt, and sometimes ale for leavening, was formed into loaves and placed inside on the oven floor using a long wooden peel. A typical oven could hold 8 to 12 loaves depending on size. The door was sealed immediately with a wooden cover plastered with clay to make it airtight. This seal was critical. It trapped heat and steam inside, creating the perfect baking environment. The bread baked purely from retained heat in the ceramic walls. No active fire. This radiant heat, from all directions, created even cooking impossible to achieve with modern ovens that heat from one direction. The baking time was typically 45 minutes to 75 minutes, depending on loaf size. The oven temperature dropped slowly as baking proceeded, but the thermal mass of the clay walls released heat steadily. The result was bread with thick, chewy crust and soft interior, infused with subtle wood smoke flavor from the walls. The efficiency of these ovens was remarkable. After removing the bread, residual heat, still 200 to 300 degrees Celsius, could be used for other cooking. Pots of stew or porridge were placed inside, where they slow cooked for hours using free thermal energy that would otherwise be wasted. This cascade use of heat energy made Viking cooking remarkably fuel efficient, despite the lack of modern technology. But bread, meat, and soup still left one critical feast component: ale. For that, Vikings used the same hot stone method, combined with fermentation technology that was genuinely sophisticated microbiology. They practiced without understanding the science behind it. The ale production began with malting, soaking barley in water to initiate sprouting, then drying it to stop the process. This converted starch to sugar. The malted grain was crushed and mixed with hot water, heated using hot stones in wooden troughs, creating wort. The wort was boiled, cooled, and left in open containers. Wild yeast from the air or preserved from previous batches colonized the liquid and began fermentation, converting sugar to alcohol and creating the distinctive flavors. This process was mysterious to Vikings who didn't understand yeast existed. But they knew empirically that following specific procedures produced good ale, while deviating produced undrinkable swill or even toxic brews that could sicken or kill. The fermentation failures were genuine dangers. If contaminating bacteria took hold before beneficial yeast established dominance, the result could be liquid that caused violent illness. The signs of successful fermentation versus dangerous contamination were subtle: smell, appearance, taste. Experienced brewers developed the judgment to differentiate, but mistakes happened. Serving contaminated ale at a feast could poison hundreds of warriors, creating disaster as severe as any cooking failure. The psychological pressure on brewers was enormous because they worked with invisible processes they couldn't see or control directly. Yet Vikings produced ale reliably enough that it was a dietary staple, providing calories, nutrition, and safe hydration when water quality was questionable. We see that Viking feast cooking was an integrated system requiring mastery of geology, thermal engineering, materials science, microbiology, and project management, all without any modern tools or knowledge of the underlying scientific principles. They developed these techniques through centuries of empirical observation, learning from both successes and catastrophic failures. Every technique, from stone selection to fire management to earth oven timing to smoking duration, was refined through trial and error, measured in ruined feasts and poisoned warriors. The cooks who survived to become masters possessed knowledge as valuable as any metalworking or shipbuilding skill. They proved that sophisticated cuisine doesn't require technology. It requires understanding materials and processes deeply enough to control them. Precisely. Modern chefs, with all their thermometers and timers, struggle to replicate the flavors and textures Vikings achieved using only observation and experience. Want to discover more lost technologies that ancient civilizations developed to levels modern science struggles to match? Subscribe to Medieval Spirits right now. We're exploring forgotten knowledge that demonstrates human ingenuity can overcome any limitation when survival demands it. Join us as we investigate how ancient Romans created concrete that's still stronger than modern formulations after 2,000 years. How medieval blacksmiths forged steel harder than industrial products using only charcoal and muscle power. How Polynesian navigators crossed thousands of kilometers of open ocean using only wave patterns and star positions. These aren't just interesting history. They're proof that technology isn't necessary for solving problems. Only understanding and skill. The Vikings demonstrated that feast cooking without any metal tools could achieve results that modern restaurants with full kitchens can't match. What other ancient secrets reveal capabilities we've lost? Find out on Medieval Spirits. Hit subscribe because the past isn't primitive. It's a demonstration of what humans can achieve when we truly master our materials and methods. And we're revealing it one video at a time.